Good afternoon from here in Paris. Thank you for joining today this global webinar. My name is Caroline Maitre and I will be your host for this event. I would like to thank you all for joining. Today's topic, we will be looking at Design Smart Connected Product ECAD-MCAD collaboration for better harness design. I am delighted to welcome as our speakers today, Mr. Chad Jackson and Mr. Paul Johnston. I will give a very brief bio of the speakers and we will be ready to start. So Chad has a Bachelor of Science in Mechanical Engineering from the University of Kentucky. As the principal analyst of Lifecycle Insights, he has published over 100 publications, ebooks and white papers, and presentations, live events and webinars since 2010. Lastly, he has surveyed over 1,000 engineering organizations as part of his research studies. Paul is an employee of Siemens Industrial Software as a portfolio development executive. Earlier in his career, Paul was with Mentor Graphics and Harness Software Limited UK and has accumulated more than 2 decades of experience with commercially successful automation software for wiring harness design and manufacture. Find out more and visit the Mentor website to read Paul's article. All right, so without further ado, I would like to hand over to our first presenter, Mr. Chad Jackson.
So the context here and the reason why it's important is that there are many companies today that are making this transition from traditional mechanical products to smart connected ones. And when you make that transition, you always have to figure out, or you make any kind of transition like that with your product, you got to figure out who's going to be designing it and how are you going to be developing those in those new engineering domains for your product. You got to put together a plan, and that certainly plays into the mechanical electrical collaboration that Caroline was just talking about. So in general, we see a lot of different companies kind of going from this traditional manual operated type of product like a push lawnmower, and you see this kind of transition right here, being transformed into an autonomous, smart, connected lawnmower, which provides a lot of features that are unique for a product. It allows for differentiation. It actually addresses a lot of the requirements and needs and interests of users out there, and it's something that can sell at a higher rate. So the question becomes, how do you develop this thing? So let's dive into that. So when you start thinking about, okay, well, how are you going to develop something like this, a smart connected product? You need to think about, well, what are the different constituent components that go into it? So first off, you see an embedded system in these smart connected products. The embedded system is composed of a combination of circuit boards and embedded software that provides either intelligent features or control. And it acts kind of like the brain of the entire product. So now if that's the brain, then when you look at antennas for these things, whether it's wireless or otherwise, this is the way it communicates with things. This might be the mouth and the ears. It's how it talks and how it listens to the internet. And often you see a lot of data that is shared to IoT platforms where you can do all sorts of interesting things. You can monitor kind of the health and maintenance of these things. You can do proactive maintenance. You can tell it to not run when it's raining, perhaps, and that type of thing. Next up, you have sensors. These are kind of the eyes and sometimes ears as well, where you can enable really important features as well. So for this type of product, you can set it up so that if it senses any moving object within 5 feet or 5 meters or 5 yards or whatever, it will shut off as a safety mechanism. So that's a good example of how you can use this type of component. Next up, you have actuated components. So these are the pumps, the hydraulics, the electrical motors. These are how the smart connected product exhibits some control over its environment and its own operation. And then you have traditional mechanical products, traditional mechanical components that are used for the rest of the product. And lastly, and very importantly, you have the electrical system. This is how everything communicates to each other. It's how the different electrical endpoints are connected. This is how signals are sent back and forth, and also it delivers power to all those electrical components so they can run. So when you start to think about, well, okay, how are we going to design this thing? You need to have competencies in all of these areas, but also at a system level to make sure that all these things work together. Now, when you look at development processes across these domains, you actually see a lot of different types of processes. A lot of hardware development uses the traditional stage gate or waterfall type of process. This is you do a bunch of work and you reach a gate in the process that requires a certain amount of requirements to be completed, whether that's product or process requirements. And when you satisfy those, you move through the gate and you go into the next stage, and you start to work against the requirements in the next stage. A very different approach is Agile. Agile has traditionally been used for software development, and is certainly being applied for embedded software. And this is very interesting because it relies on kind of flexibility or agility to be able to have different people pick up design responsibilities or development or coding responsibilities in different areas. And there are other characteristics, like you typically work on in a time-boxed type of constraint, maybe 2 or 3 weeks. And at the end of that thing, it's called a sprint, you actually deliver a working prototype of your product. And there's some interesting implications as a result on hardware development. And finally, spiral development is something that's very popular in aerospace and defense. And it kind of goes all the way from the top, from a prime contractor all the way down to some of the lowest suppliers. The idea here is that you have very simplified representations early on, and then you iteratively improve on that and spiral out and get more detailed while you're assessing a risk. So one activity that you got to figure out is, especially if you're going to have multiple competencies within your company, how are you going to align these things? How are you going to merge or meld them together? And if you're just the mechanical engineer working on your own, I guess you can pick what you want to do. But there are other considerations if you want to look at, okay, well, how are you going to transition? How are you going to make this transition if you're a mechanical engineer? So typically, I don't see companies that invest ahead of the curve. They tend to invest behind the curve. And what I mean by that is that when they realize, okay, we need to start putting more electronics and software into their product, they don't go out and hire a bunch of software engineers and electrical engineers. They ask the mechanical engineer to do it first, and as a prove-out kind of process, and then from there, they might hire in those other engineering domains. So not only does the engineer kind of have responsibility for the mechanical hardware, but also they got to start thinking about the systems. How is all this stuff going to work together? They need to start thinking about embedded software. This is another area where very simple programming, maybe visual programming, that's kind of the approach that mechanical engineers will typically use. It's being democratized. And then, of course, electrical and electronic. And if you're going to look at this, if you're going to have a mechanical engineer kind of explore these new areas, then you need some unusual traits of the tools you're going to be using, because the user is different. You know, you're not looking at a traditional electrical engineer doing the work. It's a mechanical engineer who's moonlighting with electrical engineering work. And the same thing with software, right? So the profile, user profile looks different, and that's what we're going to look at as well. So the other thing to take into account here is, as companies as you go through the transition from a digital realm to the physical realm, it becomes really important to prototype and test the systems working together. You know, is everything gonna mesh together? When you hook up the antenna through the electrical system to the embedded the embedded system, do they all talk to one another fast enough, right? Is there enough bandwidth on that electrical system? And when you think about it, all those electrical endpoints really can't be tested as a system unless you have your electrical system, your cables and your wires, because you need to physically connect them. So a lot of people have waited until the very end to develop the electrical systems. It's kind of the tail on the dog that waits until the very end. And if you do that, you're setting yourself up for very high stakes, high risk type of prototype that's being developed. And if you have failures there, then, well, you know, you're taking a significant risk for failure. So it's a far better strategy to take this on earlier in the development process, address these issues, resolve them upfront digitally, and then as you progress to a physical prototype, then you have much lower risk. You're dealing with a known quantity. So when you think about electrical systems in particular, there's really two representations here. You have the logical part of it and the physical part of it, right? So you have in ECAD, this is where you build out the net list, the from-to information, what cable carries what signal connecting which two electrical endpoints. And that's critical information, and that's kind of logical design. And then what you're going to have to do is route the wires representing those wires in the diagram. You need to route them through your 3D mechanical assembly. Now, what's interesting about this when you start thinking about a net list is that really these two representations are the same thing. Underneath them, you have the same net list, right? They're just manifested in two different ways. So you got to make sure that they agree and that they're synchronized. So that's a major, I guess, concern or objective that you need to have. The product development process and the tools that you use to do that are critically important. And that's true whether you have electrical engineers and mechanical engineers separate, or a mechanical engineer that is exploring this on their own independently. So let's talk about the tools that you can use to enable that. So traditionally what you see is file-based exchanges where the wiring schematic has been developed. You then export that and you import it into the 3D assembly model, and it kind of acts like a to-do list. You have from-to information that tells you where you want the wire routed from and to. And there's a few detriments with this approach. It's a manual effort. The engineer has to export and import. Furthermore, changes between iterations, usually it's a wholesale set of changes, right? So if you've gone ahead and imported your net list once, you need to, and there's another iteration, often you need to export and import it as a whole instead of piecemeal, instead of looking just at the individual change where it's maybe one wire. And it's not always clear what change was made visually in the design. So there are some shortcomings with this approach. Now, the implication of those shortcomings are pretty important. Usually what you see is an initial exchange of the file early in the design process. And then because it's manual, because there's a lot of effort associated with it, because change is not explicitly clear, a lot of times organizations wait, or teams, engineering teams wait until the very, very end to exchange these files. And again, you're setting yourself up for a high-risk type of situation. If you get to the end of design here, and there's a whole bunch of issues with your electrical system, you're going to be very constrained in terms of what you can do and the types of design changes that you can make. So there are big issues here, because those constraints, those problems can translate into delays in the development process, or much higher costs in the development process. Now, the alternative to this is letting the applications talk to one another. So this is a relatively new advance kind of in the industry. And what happens is the MCAD and the ECAD tool actually connect to one another, and they exchange the information about the net list. And as a result, they understand and know what changed from one iteration of the electrical system to another. So they can show a list of changes. They can highlight that list of changes. You select it, it highlights on the screen. And it's seamless, very easy, and very quick. There's no manual effort here of exporting and importing files. So this is a significant advantage. And there's some serious implications for the process as well. Because this is far easier and far faster, you can afford to update your electrical systems more frequently, and you can start much earlier. And of course, this lets you resolve design issues far earlier and, frankly, continuously in the design process, right? So you can kind of work through those issues and take care of it earlier. Now, the other thing to take into account here, there's another capability that's pretty important, and it's some people call it cross-probing, some people call it interactive highlighting, but the idea here is that you can select a wire in the ECAD tool, and the corresponding wire will highlight in the 3D assembly. The routed wire will highlight. So, okay, you might think, okay, that's interesting, but how useful is that? Well, a lot of times with these electrical systems, there are constraints from a logical perspective, meaning you can only have certain things connect to certain things, and then you have physical constraints. So if you look at, say, signal integrity, the longer the wire is, the weaker the signal gets as it travels along it. And if the signal is too weak by the time it gets to electrical endpoint, well, the electrical endpoint will not read it, right? And that's a big problem. So looking at these things, looking at, okay, well, what's connected to what in the logical diagram or schematic, and then looking at the length, for example, in your 3D assembly is pretty important. And understanding which wire is which in each helps you resolve those issues, helps you resolve the conflicting constraints across physical and logical aspects of the design. So, the same thing we talked about before applies here. You can work through these issues. You can either it's mechanical engineer on their own working through it, or it is the electrical and mechanical engineer that are collaboratively resolving these conflicting constraints. This is a tool that can enable them to do it far faster, far easier, and throughout the process. So yeah. So let's recap here. There's a few takeaways here. So a lot of mechanical engineers are being asked to take on new and interesting responsibilities in the development of smart connected products. And when you look at that, their profile for use is very different than just an electrical engineer and a mechanical engineer. As a result, because the mechanical engineer won't be in this tool all day, every day, it's got to be easy to use. You got to make it easy for them to pick it up and use it and be productive immediately. Another thing is when you look at functional checks, whether it's constraints, rule requirement satisfaction analyses like signal integrity, you got to make it easy for them to perform those rule checks and those analyses. That's another characteristic of a tool that's really important. And finally, integration between ECAD and MCAD is really important to help resolve the conflicting constraints and collaboration between those domains. So those are the things you should keep in mind as you're thinking about, kind of making this transition and having mechanical engineers take on these responsibilities. So with that, I'd like to hand it over to Paul.
I'll be providing some evidence that solid edge wiring and harness design addresses some of the best practices that Chad was saying in modern tools should be attainable. So first, just a brief introduction about solid edge wiring and harness design. Solid edge wiring design is a schematic tool for designing wiring diagrams, and solid edge harness design is unsurprisingly an environment in which fully engineered harnesses can be released for manufacturing. So there's a drawing element to that as well. They exist in the solid edge family with solid edge routing and solid edge mechanical to come together as a unified environment in which the electrical CAD domain and the mechanical CAD domain can collaborate. And there are collaboration tools in keeping with the kind of features and functionality that Chad spoke about. So my presentation will start off at a canter, it will accelerate to a gallop, and it will be a race through some highlights, some advantages of this solution, solid edge wiring and harness design. So we'll emphasize first electrical and mechanical collaboration, which is an important benefit when it's attained. And then the middle sections will highlight some areas of intelligence in the solution. People talk about intelligent drawings, intelligent CAD drawings these days, and intelligence behind the drawings. And I'll explain some of the functionality as it relates to that, and included in that will be touching on some process discussions and workflow. So because it will be a sprint, I'll endeavour to give you a summary at the end, and there'll be time for question and answer for both Chad and myself at the end. So first, the collaboration between mechanical and electrical. This is a stock photo, but it struck me as being appropriate because the two people kind of sat looking at one screen, which is what we're just about to see in a moment. And the question in my mind is, which one of these two people is the electrical engineer? I kind of I answer this by saying, well, usually it's the person that looks the most worried of the two, right? Because the electrical engineering discipline comes in right at the end, and is most vulnerable to late changes. So maybe this woman is just pointing out to the mechanical engineer that a repackaging of some mechanical elements will necessitate a late rerouting of the harness. So how, as Chad says, how you can deal with this is a number of techniques. You can pass files back and forth, or this is solid edge mechanical and solid edge wiring design co-controlled by two people on one screen. The split screen that we're showing is a brief demonstration that will last about 45 seconds of cross-probing, cross-highlighting. So this is split screen. It could be two engineers sat at opposite ends of a building, or even tens of miles away or in the next state, collaborating via a web meeting, just like to a certain extent you could say we're collaborating a web meeting here. What's just happened is the mechanical model has been queried, and that connector was highlighted, and it highlighted red in the other domain. And the same has happened the other way around. So this connected mode is an instantaneous feedback to answer some of the questions about routing, packaging, and to synchronize naming and between the two models. This is a somewhat high-level view of the type of workflows involved. And you notice that, just to pick up on something that Chad said, in this diagram, I've drawn three engineers: a mechanical engineer down here at the bottom, who's in charge of the 3D CAD environment, and then responsibility split between a wiring engineer and a harness engineer. Sometimes, on rare occasions, I've seen this all located in one single person. One example was, I can think of as an autonomous driving system environment where a mechanical engineer had the knowledge and the enthusiasm, and because it was a startup company, also acquired the responsibility for electrical design and packaging. So it could be one person, but more commonly it's two. I mean, the wiring and harness engineers is quite often the same person, but certainly in larger organizations, there may be a split between manufacturing and architecture. So you see in the wiring design and harness design boxes that it's quite common that at least one of these drawings is the kind of document of record for these engineers, which they, without cross-probing, without cross-highlighting and co-piloting, would be sitting down and sharing the details with a mechanical engineer who may or may not be enthused to read an electrical schematic. So in this in this collaboration, this is showing on the left side a wiring diagram, on the right side a harness diagram. I want to pick up on something that Chad was saying about the privacy of the net list. Essentially, it's different aspects of the same meta information that through the life cycle of the product gets trafficked to and from the mechanical system. In the previous diagram, we saw bidirectionality. And the potential here, because it is a straightforward, a clean process that happens kind of very quickly. It can be done over a conference call or with a 20-minute meeting of engineers starting. But it can be done, like Chad said, as needed, so that it's supportive of kind of agile and spiral product development philosophies. It certainly will not take days of people's time manually checking lists of things for agreement. I would point out some differences in the life cycle. First of all, connector part numbers. What's the advantage of having the connector part numbers for the assembly. I identified early in the process at the time you're doing wiring diagrams, before you fully physicalized it into a harness interconnect. That gives a tremendous advantage in previewing the logistics for manufacturing, and potentially it can reduce the burden, the cost of freight because of long lead times for connectors and the difficulty of obtaining them for manufacturing at short notice. This is one of the reasons that we time and again talk about late changes being very expensive and very dangerous and very risky. The earlier you can do things, the better, and this technology enables that. So finally, whilst we're talking about mechanical and electrical collaboration, I'm just going to make a couple of remarks about this slide. One is that it refers again to a very common problem, that of collision detection or interference, sufficient space for the wiring. There's a safety and quality aspect to that, because if space is too tight, you get, especially with vibration in certain equipment, you could get rubbing of the protections, and maybe shorting of the circuits. And to reroute normally means longer wires. Longer wires mean greater lengths mean heavier weight, and so on. If you've got cost and weight targets, then you can get into trouble later. ECOs, if approximately $1,500 per ECO is what the result is, even reducing by 20–25% using this technology, the ECOs that squirt out at the end of the process, whether you're making mining equipment, industrial machinery, whether you're making ambulances or other consumer goods, there's money to be had in reducing engineering changes, getting things right first time. And then something that I mentioned before, to minimize the amount of manual effort in checking lists and manual validation. The people that do this design are creative, they're expensive, and you want to optimize your human resource, because otherwise they may want to leave for a more interesting job. That's one of the motivations. Okay, so as promised, I'm going to go on to take a really quick review of some of the features of solid edge wiring design and harness design, and I'll kind of go back and forth between the two to make the point. The environment is, the user interface is is standard. So what I say to one generally will apply to the other, unless I state otherwise. So I'm just going to superimpose some call-outs on this, a picture of the wiring schematic drawing tool environment, and explain that as well as the drawing having data behind it, and therefore you could say that the drawing is intelligent, the application itself is pretty smart. I'm pointing here at a toolbar button for a slicing feature. This particular design that I've done a screen capture of has multiple sheets, at least 6. And typically when you're over the months and years adding to these, adding new electrical and electronic components, different actuation methods and so on, and control units, then quite often you have to, because the real estate gets cluttered, you have to transfer off some elements of the drawing to another sheet. So the ability to grab objects and transfer them easily with the same references to another drawing is provided. The definition of specialist multi-core cables, we put an effort into this a couple of years ago to quicken the process, because we realized that users were perhaps spending maybe 10 minutes editing a drawing to fuse the information with what was in the library for specialist multi-cores, especially complex ones, where you have jacketed multi-cores within other jacketed multi-cores. Now, if we could reduce that 10 minutes, say, to 3 minutes, that would be 7 minutes given back to an engineer. If the engineer was doing that 6 times a month or 6 times a week, then that was a significant saving. And we invest in not just this one feature, but there's several like that, which are out-and-out time savers. The part selection dialog, we put a lot of effort into being able to filter, and we have an approach that you shouldn't have to search for more than a few seconds to find anything in your database, even if your database has thousands of symbols. Here's one of them previewed, and thousands of devices and connectors. This symbol preview, I've highlighted that because you have a double click and you can drag it onto your drawing, and with key clicks R to rotate it, for example, you can spin it around and have it the right orientation. So the design object browser, there's a lot of engineers are visually oriented to understand the schematics, but especially younger engineers are more used to IT functionality where you can search. And the design object browser will filter down potentially hundreds of objects in your design and get you to the one that you're interested in. Here are design checks. We'll go into a little bit more detail later. They are can be run so that they're always on, or they can be temporarily suspended with this button here on status bar. And this tabulated information can tell you if you are making a simple change and you make the simple change wrong, that you are in danger of destroying the integrity of what was previously a good release design. Okay, so that was a snapshot of just a few of the user interface functions. There are plenty more of them, and as well as the underlying rich data, the application itself is pretty smart. So the underlying data can go to the depth that you can do qualitative and numeric simulation. I've just pressed play on this short video. Again, it's less than a minute, and you will see here that you can, in this environment, change the actuation, the switches off and on and so on, to see whether the circuit still functions as desired. You can change those device parameters, and there is evidence of numeric simulation. So if you have, as Chad alluded to this, if you are concerned about voltage drop, if you think that you may have wrong-sized the fuses or the wires, you can inspect the design, see what current is being drawn at various places. Now, notice that all of this is being done, this simulation is being done without a prototype being built. A physical prototype is not necessary. A properly validated design is necessary. This design has been properly validated, but this is prior to building a physical prototype. So you can save a lot of money by using that functionality, and that is the depth to which this system is smart. Here is another piece of intelligence. The intelligence that comes from separating the style of the drawing, the pictorial representation from the underlying data. This is a very brief dip into an area of functionality called diagram styling. This happens to be a harness print, the same for the wiring diagrams as well, and form board one-to-one representations of the drawing. A simple thing that I'm doing here on the test drive environment is I'm changing the default style so that the takeout to takeout dimensions are changed to orange color and are encased in an oval shape, therefore distinguishing them from the node to node dimensions, which are styled to appear below the bundle line. And I've just applied that to the entirety of the drawing. So I've gone in and edited. The advantage of this, what's in it for you, is you can make the drawing appearance conform to this, the way the consumers want it. And also, in this styling, you can automate the positioning of many of the many, if not most, and hopefully nearly all of the entities on the diagram, so that you don't have to push things around manually, so that the placement is automated and you spend time designing rather than spend time editing a CAD output. The next thing I just want to touch on is the end goal of both wiring diagrams, the end point of both wiring designs and harness designs is manufacture and manufacturability. There is, as I've already mentioned, a foam board drawing capability in solid edge harness design. There's also the potential here for you to decide what makes sense in terms of when to hand off, what to hand off, and to whom to hand off. You may be reliant on contract harness suppliers. You may want to specify more of the componentry rather than delegating responsibility to your harness manufacturers to choose certain components that go onto the harness, like the tapes, for example. What opens up this potential is because you're always getting down to the release stage with validated correct by construction type data. I'm just going to give you an example of this. This is another quick example, and this is kind of deceptive because what's going on here is potentially many hours of work. This, what you're going to see, that's just producing a kind of before bill of materials, there'll be an after bill of materials. And what's going to happen in the interim is terminals and other cavity components will be selected and added to the bill of materials on this harness. So there's a function for that. Terminals have just been selected for one connector there. I'm going to switch to access the same program and the mode for all connectors on the harness. And what has just happened is that the process has gone and taken a look at the library definitions, the connectors that are used on this harness, looked at the terminals that are appropriate to those connectors, looked at the wires that are placed in the cavities in that connector on this drawing, and seen whether there is a terminal that fits also within constraints like a few of the terminals are specified on this harness as needing gold plated. So you can see the process is very fast, and it's covered also by exception reporting from the design rule checking. If no terminal is selected, you can override. The override is itself the subject of a design rule check. Talking of which, we'll move swiftly on to design rule checks. Here's an example back to the wiring diagram environment. This is the same in the harness design portion of Solid Edge as well. I've left on the screen here just one blue line for I filtered down the error messages on this half-finished schematic. And what's going to be shown is this one design rule check shows a one-ended wire, which is not something you want in your design. So you click on the hyperlink in the message, and it zooms the diagram to show you the item that needs to be addressed. I have decided to address this failure by joining that wire to another one and making a splice. That may or may not be a good design that results. When I save and rerun the design rule checks, or if the design rule checks are always on, I will be told whether I've made an error or not. So that was just one design rule check. Obviously, if there's more than one, you can go through them systematically, and the system helps you towards the resolution of whatever anomalies there are. Okay, so finally, when we're talking about the intelligence that's imbued in this system, I do want to talk about a library, because rather than intelligence from libraries, you get wisdom. The library is split into two parts. There are symbols, symbol management and symbol maintenance. You can import DXFs. There are approximately 1,400 IEC and ANSI symbols provided. There is an example library of harness components, including connectors where the position of the cavities is marked, say, ready for form board colorization and leader lines and so on. In this, as well as symbols, the facts about components it can be maintained in the solid edge electrical parts environment. We're just going to have a look now at the maintenance program and choose a connector and just have a look at a couple of things in the connector. Again, this is just a surface treatment. We'll talk about how you can learn more in a moment. So look at this connector. It's characterized in the description there. It has the symbol associated from the electrical part symbols. And then this tab for housing definition, the subcomponents. Now we saw the subcomponent selection algorithms running. This is kind of simple. It only has one terminal, one cavity plug, one cavity seal, one cable seal, and it has a cover and locking piece as well. The query that was just run was to show where the connector has a number of, where the connector has devices that it mates to the harness side connector, what we call a footprint. Okay, so there's the promised summary. Since you can all probably read this faster than me, I'm just going to summarize the summary by saying, Chad talked about designing smart connected products, and essentially what I think we've produced is a smart connected application to help you design those products. And because we talked, I talked at a sprint about the product, I want to show you this. This is an example of the mechanical product with the electrical interconnect that could be designed in this environment, and that's the purpose, right? It's not that important to us that there are cool features in the software. What is important is that customers get use out of it, get value out of it. And that's why we return to that slide. This is a summary of how products are organized. The interplay with electrical routing and mechanical design is something I mentioned at the start. And this is the final slide. There is an extensive training library. We just added another 16 videos to it. There's a taster or a free trial of the training where you get an online virtual lab environment, i.e. a sandpit or an R&D version of the database and the application for you to try out. the short videos that I did in this presentation were mostly done in that environment. It's more or less fully functional. And just one closing thought, which is that there's, as people change processes in this sort of work, it's easy to kind of get lost in a forest of new ways of working and so on. What I recommend to all the customers that start off is to capture a vision, find some ways of measuring your progress towards it, and work that way. So you've got some roadmap basically, and some metrics to guide you through the adoption of software like this, because you're going to get a lot of value out of it over quite a number of years.
All right, so thanks again to our presenter today, Mr. Chad Jackson and Mr. Paul Johnston, and thank you all for joining. With that, the session is closed. Goodbye.